Hey guys, in this video I wanted to get into the details of the case setup in Converge. So far we have been setting up a few simulations and some of the options have been skipped. So today I wanted to go through some of the options in detail because that helps you understand the whole simulation environment much better. So I'll start with the applications tab. Now when you open up the applications tab, on the left hand side you have the categories and on the right hand side you have the applications. Converge was primarily an internal combustion engine solver, and hence we have a dedicated application for that. So any other type of simulation that you want to set up has to be done by clicking on general flow. Okay, I hope that makes sense. The other thing that you can do is on the left hand side you have all these categories. So for example, you can select the materials that you want. Under simulation parameters you can include the parameters that you want. For example, if you want to include gravity, you would enable the body force. Similarly, in the boundary conditions, you have some advanced options. So you will not be using these two options. These are quite advanced. So for example, GT suite coupling enables Converge to be coupled with the software called GT Power, and wall value initialization is a concept that allows us to initialize quantities on wall boundaries. Okay, so moving on, let's go to initial conditions. So in initial conditions, by default, we set up only regions and initializations. But then there is a concept called events. So events is used whenever you want to connect and disconnect two regions. All right. So for that, we will be setting up a shock tube problem soon where you will understand the concepts of events and how they actually work. Mapping is an interesting concept that allows you to take data from either an existing simulation or from experiments to initialize your simulation. When we initialize the domain, we basically give a particular value for pressure and temperature, right? Now let us say that you have data from some other software where the pressure and temperature is provided at each and every point. If you want to take that data and feed it into Converge, you would be setting something up called as mapping. Then comes physical models. So this is a list of physical models that Converge provides. So depending on the simulation that you want, multiple physical models might be required. Now remember, you cannot just check all of them together because you cannot run a simulation which uses all of these physical models. All right. Then comes grid control. So under grid control, this is where you set up your base mesh, which we have already done. We did take a look at adaptive mesh refinement, and we also looked at fixed embedding. Grid scaling is something that you did when you set up the channel flow problem. So grid scaling helps us change the base grid as a function of time. Finally, output and post-processing. Here we don't typically change, we use both the options by default. And then finally, user-defined functions. So UDF is something that helps us write our own code to do custom calculations. Now we are not going to be using UDFs in this particular course, so I'm not going to be talking about that. Finally, surface checking, it's enabled by default. So this is your geometry diagnostic tools that's available for you. The next thing that we are going to be looking at is gas simulation. So when you set up your gas simulation, you will see that initially you set up your equation of state. Now you can use an ideal gas model or a real gas model. So ideal gas model means PV equal to nRT is going to be used, or you can employ one of the real gas models. So Redlich-Kwong is quite famous and Peng Robinson is also quite famous. If you're interested in learning more about these models, I would recommend you to read the Converge theory manual. All right. Then you can see that there's something called as gas thermodynamic data. What is that? Well, in order to perform CFD calculations, especially if you have gas species, you need to know the entropy, enthalpy, and specific heats for all the participating gas phase species. Converge provides you a database of 621 species. For example, if I click on a species, you can actually look at its specific heat, enthalpy, and entropy. All right, as a function of temperature. And there are so many species that are available. You can just click on them, click on the graphs, and look at the properties if you want to. All right, now where is this data coming from? This is coming from something called as a NASA thermodynamic data file. Okay, so the NASA thermodynamic data file contains a list of polynomial coefficients that can be used to calculate these properties accurately. Similarly, if I click on gas transport data, that contains the viscosity and conductivity for the gases. So let me just close this and click OK here. All right, the next thing that you will see is something called as a reaction mechanism. What is that? When you run a converge simulation, if combustion is involved, then you need to provide something called as a mechanism file. So far, we have not done any kind of reacting simulations. That is, we have not done any simulations where combustion is involved. So we don't need a mechanism file. However, if I click on this little icon, you will see a preview of the mechanism file, which is called as mech.dat. You can see that it contains elements, species, and it has a reactions keyword, but then there are no reactions, correct? So when we set up our species here, Converge knows that O2 and N2 are the participating species, right? So that is the only information that is being used from this file because there are no reactions in this particular file. That being said, another thing that I wanted to tell you, which you might have already realized, is you are actually using Converge Studio to generate a bunch of input files. You can see that in order for you to run a Converge simulation, you require the .in and .dat files. So these are the files that are going to be read in by your solver in order to do the simulation. Okay, so when you are actually going through the case setup tree, what you are doing is you are editing these input files. For example, if I click on gas simulation one more time, and if I click on this little guy, you can see that this window is being used to edit the inputs.in file. All right. So similarly, if I select something else, for example, run parameters, and then click on this preview, you can see that this is also being used to set up the inputs.in file. Because the inputs.in contains a lot of properties, so you need multiple dialog boxes to set it up. And those dialog boxes are shown at different locations in the case setup tree. All right, now let's take a look at simulation time parameters. So your simulation time parameters controls from what time to what time you want to run the simulation. So that is your start time and end time. You should be quite comfortable with that. In addition to that, you also set up your time step control parameters, which are basically all of these time step multipliers. Anytime you see a time step multiplier or a limiter, these are factors that are going to control the time step. Now at this point, the only takeaway that you need to go with is when the time step is large, your simulation is going to run faster. When the time step is small, your simulation is going to run slower. Okay. Now a smaller time step means that the accuracy is also more, but for engineering simulations, we want to make sure that we run the simulation as fast as possible without compromising too much on the accuracy. All right. Then we are going to be looking at the solver parameters. So Converge uses something called as a PISO algorithm. Okay. So PISO algorithm offers a way for us to solve the Navier-Stokes equations along with additional transport equations. We will be discussing this algorithm in detail at a later lecture. In addition to this, Converge uses a finite volume method based discretization, for which we need to basically have convective flux schemes, and we also have flux bending fractions, and then we also have flux limiters. For example, here's a list of functions that are available. Now, as far as what these functions do, we will have a very gentle introduction to finite volume method. It's not going to be a comprehensive session, but it should give you a fair amount of idea what these methods do. Okay, and then you can see that for each of the equations, right? If you take momentum, species, energy, density, you can set up the same the convective flux schemes and the flux limiters. So, and the same thing can be done for turbulence as well. So as far as the equations are concerned, these are the equations that you typically solve. You solve your momentum, pressure, density, species, passives, TKE, epsilon, omega, and then radiation. Now, not all the equations might be solved in a simulation. It depends on what physical models you're using. All right. So for each of the equations, a particular solver is chosen and solver related properties are provided. You can see that Converge uses SOR or something called as by CG stab. So this is actually called as preconditioned. This is actually a variant of the conjugate gradient method. And you can see that for all the equations, I basically have the same structure. And depending upon the solver I use, the time it takes to solve a particular equation will change. Okay, so let me click OK here. As far as the boundary conditions goes, we have talked about a few different types of boundary conditions. For example, we have looked at interface. We have looked at 2D. We know what inflow, outflow, and wall boundaries are. We still have to talk about periodic and symmetry boundary condition, which we will be doing at a later point. And here also you can actually click on this little preview icon and you can see that there is a file called boundary.in. Now this is the file that actually contains your boundary conditions. And for each boundary, there is a block of data which basically represents the conditions for velocity, temperature, pressure, and species. Okay, you can just scroll through it and then try to understand what each of the terms mean. For example, here we are saying that pressure, we are giving a Dirichlet boundary condition and the value is 1.5 bar. If you're putting square brackets, that means it's actually total pressure. All right, so let me close this guy. So with respect to regions and initialization, as I said, the next problem that you're going to be solving is actually a shock problem where we will be having two regions and then we'll be using something called as events. Okay, and with respect to physical models, these are the available models, and depending upon the problem, different models will be used. All right, finally, grid control. So with respect to grid control, you can see that there is several grid control options: base grid, adaptive mesh refinement, fixed embedding, and grid scaling. So let's click on fixed embedding. We have already played with the boundary embedding option. So if I click on this preview button, you can see that we are setting up a file called embedded.in. Similarly, if I enable adaptive mesh refinement and click on AMR and click on the preview button, you can see that this is being used to set up AMR.in file. All right, so it's a very good idea to familiarize what are the input files that Converge has and try to understand how these input files are edited by the various dialog boxes that Converge Studio provides. Okay, another thing that I wanted to point out is, for example, let us say you are in this particular window and you need some help. You can just click on this help icon and that's going to immediately provide you help that is relevant to this particular window. You can just read about it and then try to understand what's going on. So instead of you going into the manual and searching for information, you can just open this up and then read through it fairly easily. With respect to output and post-processing, we are not going to be discussing anything new. We have already covered that in detail. User-defined functions is something, as I said, it's not included in this particular course, but this actually helps you develop your own submodels that you can actually integrate into Converge. In addition to that, user-defined functions can also be used to do custom post-processing and data extraction. Okay, all right, so I hope you enjoyed this video and it provided you a little bit more information about the workflow in Converge. We will be having multiple parts of this video. We will be having similar videos in the future. If you have questions, get in touch with us and I'll see you guys in the next video. Bye.